Yes, so let's move on to the next chapter, which is Laplace transform. So before we go into the details of the Laplace transform, first we'll understand why should we study Laplace transform. So to do that, to understand why we should study Laplace transform, we will go a little bit into the previous chapter, which is the last part of continuous time Fourier transform. Hopefully that will give us the motivation why should we study Laplace transform. So what is it we have seen in the last topic here? We talked about LTI systems. Okay, so let's consider LTI systems in CTFT. Okay, so LTA systems in CTFT. Okay, so that we will understand what happens there. So if you remember, for any LTA system, the output for any LTI system, the output is given by what here? For any LTA system, we know that y of t, which is output, is equal to the input x of t convolved with h of t. Correct. So we know that for any LTA system, the output y of t is equal to x of t convolved with h of t, where x of t is the input and h of t is the output. So the block diagram representation will look like this, right? So this is our LTA system with impulse response h of t, and this fellow will give us y of t as output, which is equal to x of t convolved with h of t. Okay, so to understand the frequency content of a signal, what is that we have to do to understand or to do frequency analysis? So to do frequency analysis, we have to go for CTFT. Okay, so we have to go for CTFT. Okay, so what frequencies are passed through the system, what frequencies are not passed through the system? To understand all that stuff, we should know the frequency content of a signal. So how do you get the frequency content of a signal? By taking the Fourier transform. So that's the reason to do frequency analysis, we have to use what is called continuous time Fourier transform. But in CTFT domain, okay, so in CTFT domain means in frequency domain. Okay, so in CTFT domain, okay, if you assume this equation 1 becomes what? So in CTFT domain, so 1 becomes y of j omega equal to x of j omega multiplied with h of j omega. Why? Convolution in time domain is equal to multiplication in frequency domain. So if you multiply the corresponding Fourier transforms, you get the output. But to find the Fourier transform, or for x of j omega and h of j omega to exist, what should happen? The both signals x of t and h of t should be absolutely integrable. Okay, so to get this, what is the condition? We wrote that is very good, but when will they exist? So to get this, both x of t, to get in this in the sense y of j omega. Okay, so both x of t and h of t should be absolutely integrable. Should be absolutely integrable. Okay, so should be absolutely integrable. Okay, right. So implies what? Integral minus infinity to infinity mod x of t dt is less than infinite. Correct? First Dirichlet condition. So we assume other two conditions are satisfied by default. Okay, and integral minus infinity to infinity modulus of h of t dt should be less than infinite. Okay, so both x of t and h of t should be absolutely integral. But let us focus on this fellow. Okay, so integral minus infinity to infinity h of t dt, modulus of h of t dt is less than infinite. So this implies what? This implies the LTI system. Correct. So the LTI system is is stable. Okay, that's what we have studied in second chapter. What is that? If the impulse response of the LTA system is absolutely integrable, then we say that the system is stable. Okay, then we say that the system is stable. So indirectly, we can do frequency analysis of an LTA system provided that system is stable. Okay, so that indirectly, what does it mean? This implies frequency analysis. Okay, so frequency analysis of LTI systems. Okay, so frequency analysis of LTI systems is possible only if the system is stable. Only if the system is stable. Now question arises. What happens if the system is unstable? Okay, if system is unstable, Fourier transform will not help, and hence we have to go to another transform. Okay, so hence, in other words, we'll write down that. So in other words, if the system is unstable, okay, in other words, if the system is unstable, in other words, if the system is unstable, what will happen here? Fourier transform will not help. Okay, so Fourier transform will not help. Okay, hence we have to look for another transform. Hence we need help of another transform. Okay, another transform. To study or to analyze. Okay, so to analyze which system here? To analyze unstable systems also. Unstable system. Okay, so we can use another transform to analyze stable system also, but for stable system we already have what? Fourier transform for doing the analysis. But if the system becomes unstable, what will happen? Fourier transform will not help, and hence we have to look for another transform which will help us in understanding the intricacies of an unstable system, and hence we have to go for what is called Laplace transform. Okay, the transform which is of our help. Okay, the transform which will help us, so which helps in understanding. Okay, which helps in understanding. Okay, unstable, I don't say unstable, we can do stable also, but just for motivation we will say that. Okay, the transform which helps in understanding unstable systems. Okay, unstable systems is Laplace transform. Okay, so is Laplace transform. Okay, so this fellow will help us in understanding, okay, the intricacies of which systems are unstable systems. Note that Laplace transforms also can be used to understand stable systems also. Okay, so this is like generalization of Fourier transform. So hence we can see this as, okay, this acronym, let us call it LT in this chapter. Hence, what do we say? Laplace transform is generalization. Okay, it is generalization of Ctft. Okay, Ctft is only for stable systems, but if you want to take care of both stable and unstable systems, we can take Laplace transform, and hence we'll say that what? Continuous time Fourier transform is like a subset of Laplace transform. Okay, so definitely they are closely related. So Laplace transform and continuous time Fourier transform are closely related. That we will see in the coming lectures. Okay,